All right, let's get the show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1108. I made some announcements in the last class, which I'm not sure if I should make in this one, because I'm not sure. So, Tommy, is your group doing project 2 or project 1?
My group is doing project 1.
Oh, okay. All right, so I don't have to talk about it then. I was going to make a comment on project 2, but the only other group doing project 2 in here already met with me in office hours, so you guys kind of know what the deal is already. All right, awesome. We'll just jump into it then. Yeah, the sort of things I was going to mention was the sort of things I mentioned with that group in office hours, just to give some general info. But that's not necessary. Moving very slow over here. All right. So last time, what were we talking about? We were talking about conditional probabilities. We did it like the hard way, and then we showed that there was a nice formula for it. So this is the formula for a conditional probability of A given B. What this is the probability that A will happen given that you know that B already happened. So that's what this guy is, the probability of A given B. And we know now that that is the probability of A and B divided by the probability of B. So it's a conditional probability, which is a very important kind of probability. A lot of times probabilities do depend on conditions. We know that this happened. Now what are the chances that this is going to happen is a very common thing that we need to know. We also spoke about independent events. Two events are independent if they do not affect each other, but that is not the definition I want you guys to know. I want you to know in terms of equations. So we know if they do not affect each other, the probability that A will happen given that B happens is just the probability that A will happen. Who cares that B happened, right? As long as they're independent. So by putting in that formula, we can derive that the probability of an intersection is the product of the probabilities if the events are independent, not in general. So that leads to this box right here, which is very important. And if you want to prove that something is independent, what you have to prove is that one of these equations hold. If you want to prove that something's not independent, what you have to prove is that one of these equations do not hold. We also spoke about mutually exclusive events, and these are events that cannot occur simultaneously. They cannot occur together. It does not mean that one affects the other necessarily. It just means that they cannot occur together. And so that means that the probability of the intersection is 0. A and B cannot happen at the same time. So that led to this box of formulas, also very important. So if you want to show that something is mutually exclusive, you have to check that these equations hold. If you want to show that it's not mutually exclusive, you'd have to show that these equations do not hold, or one of these equations. If you're told something is mutually exclusive, it means that you can use all these equations. By that, the same token, if you're told something is independent, it means that you can use all these equations, right? It goes both ways. We did an example talking about that. All right, cool. And I left you with an example to do. So that's what we're going to kick off today's class with. We're going to start that example, or do that example, rather. So here is that example. Did you guys try it? What is the guess here? What do you think the answer is? In Newport City, 40% of the population is male, 60% is female. Of the men, 50% smoke, while only 20% of women smoke. Suppose a smoker is chosen at random. What is probably that the smoker is male? What did you guys guess?
I wasn't too sure how to set this one up, not gonna lie.
Okay. Did you have a guess though? Did you do something but you're not sure if it's correct, or did you just not do anything?
I looked at it and I really had a hard time of just like trying to find what to use, like which numbers to use
Yeah,
where.
oh, well, do you know what you're looking for? Maybe we should start there.
Well, yeah, like you're looking for the probability that the random smoker of the 40%, is a male.
Right, but tell me in terms of formulas, what does that P of what?
Yeah, I think that's what I was kind of confused about.
Yeah, so that's the first thing. We have to know what we're looking for. So what do you guys think? What are we looking for? Can anyone state what we're looking for? Let's say let M be the event person is male. Let F, which we can call M complement in this case, be the event person is female, not male here. So for the purposes of the class, like we only have male and female, and let S be the event person is a smoker. Okay, so given that those are how we're labeling it, what probability are we actually looking for? Right, so there is a question that's given in the last sentence that, right, that's where we were asked the question. So what is that asking us? What probability? Right, so if I were to say we want probability of, well, that's the first thing we need to figure out. What are we looking for? We can't find it if we don't know what we're looking for. Well, what do you guys think?
Is it like male smokers are conditional to how many males there are?
And male smokers are conditional to how many males?
Like if the 40% of the population is male.
Yeah, no, I don't mean you should solve the problem. I just tell me what we're looking for. P of what?
We're trying to
What
find
yeah.
P of S, but in the male form.
Yeah, but P of S, but in the male form is not a thing that we write, right?
No, yeah, I know that.
Yeah, so how would you state it?
Is it as, like, do you want it in the conditional form?
Yeah, yeah.
As conditional that it's male, so M.
So yeah, we want S given M. Is that what we want? Who's the given here? A smoker is chosen at random. What is the probability that the smoker is male? Which one is the given event?
The smoker.
The smoker, right? The smoker is what happens first. We chose a smoker first, right? We gathered all the smokers. That is the event that happens first. Right? So given that we're choosing from the set of smokers, what is the probability that we chose a male? Right? So that's the first thing. We need to know what we're looking for. So this happened before that. So this was the given, and this is what we want given that. Okay, so that's the first thing. You have to figure out what you're looking at, right? So there's some interpretation to the problem here. So now, let's see what we're actually given. We know the probability of being male and female. So we're given that the probability of M is 40%. Probability of not being a male is therefore 60%. So we're given that. And we're given that the probability of, so when we say of the men, 50% smoke, what probability is that telling us? P of what? Of the men, 50% smoke.
Is that of the men in Newport City?
Yes, yeah. How would I write that down in symbols? Like what was I just told in terms of a probability symbol? If I say of the men, 50% smoke, what probability did I just tell you? So I looked at all the men, and then I determined that 50% of all the men smoke. So what is that? Any guesses? So basically what we're told here, this looks starting to look very lean. Is given that we're looking at a male, the probability he's a smoker is 50%, right? Of the men, 50% smoke, which means the event that we're looking at men has already occurred. Then we look at the event that they are a smoker or not. And so that's a conditional. On the condition that we're looking at a male, the probability of being a smoker is 50%. We're also given that 20% of women smoke, which means if you're looking at someone who's not a male, the probability that they are a smoker is going to be 20%. Now, of course, this implies by complement probability that, okay, if I'm given a male, the probability that they smoke is 50%. So the probability that they don't smoke is also 50% because it's 1 minus that other probability. And given that someone is not a male, what's the probability that they don't smoke? Well, it's 1 minus the probability that they do smoke, and that's 80%. Okay, so this is what we want, and this is what we have. Now, I mentioned that you could use a pictorial way to go about this. So let's say we want to do tree diagrams or something. How would that work? What would that look like? So how would this branch off? Okay, so the population is at this point right here. How did we start segmenting the population? Well, we did in male and female, yeah? So we have, going over here, male. And we know the probability of that is 40%. Or we can go female, probability of that is 60%. Now, once we have the males, we can branch off. So this is here, given that we're on the male branch, what is the probability that they're a smoker? So this is smoker, if male, and that is 50%. And then we have non-smoker, if male, which is also 50%. Right? So this is the event M. This is the event S given M. And this is the event S complement given M. Okay. Now for females, we could do the same thing. This will branch off here and here. So there's a possibility that you're a smoker if female, right? So that is the probability, given that you're not a male. What is probably that you're a smoker? Well, we know that's 20%. And we have non-smoker if female. So that is the probability that you don't smoke, given that you're not a male. That's 80%. So this here is the event of S given M complement. This here is the event S complement given M complement. This here is the event male complement, right? Or female. Okay, so that would be what the tree diagram would look like. We would break it into male and female, and then smoker and non-smoker. That's how the question was presented. Okay, so that is that. Now, we want the probability that, given that I know someone is a smoker, what is the probability that they're male? And we know that that is equal to what? What's the formula for that? How do I compute that probability? What's the formula? What am I looking for? It's the main formula I gave you last time. So we need to first figure out what we're looking for, and then we have to figure out how we're going to get it. Like, what is the formula? What is the method? What is the strategy? But we have a formula for this. So what is that?
It's the probability of A intersect B over probability of B, or I guess this M intersect S over the probability of S.
So this is probability of M intersect S over the probability of S, right? Now, we don't have either of those given to us. Okay, so now the question is, how are we going to find them? Now, here's something that you can note. For instance, if I were to look at the probability of S given M, right? Well, that's going to be the probability of S and M over the probability of M, right? So this actually means that I can write the probability of S and M equals the probability of S given M times the probability of M, right? It turns out the AND probability can be thought of as a product of those two probabilities. And that's actually true whether they're independent or not, by the way. So that is somewhat of a general formula for the AND. That's always going to be true. I can use that same kind of reasoning down here. So this is going to be the probability of S given M times the probability of M. Right? That's what we just derived over here. Okay. Which basically that's why it was, and this is why I've told you this before, multiplying along an arm in a tree diagram gives you the AND probability. And this is why multiplying along an arm gives you AND. Because notice what we just did. We're multiplying along the probability of M and the probability of S given M. That's like we're multiplying along here. I'm just going to take that 40% times the 50%. Right? So that's what that's going to be. Now, what is the probability of S? Well, to get a smoker, there are two ways in which you can get a smoker, right? If you look smokers be in red, for example. We can have a smoker given that they're male, or we can have a smoker given that they're female, right? There are two ways to get the smoker. Okay. Now, these two arms are different arms. They're not overlapping, right? And you can't be both. You can't be on both arms at the same time, which means we can add them. So what we would do is we would multiply along these arms and then add the answers together. So ultimately what we're going to do here is realize that to be a male and a smoker, we just multiply along these arms. This is going to be 0.4 times 0.5. And then the probability of a smoker means I can go along that same arm, which is 0.4 times 0.5 plus the probability of going along the other arm, which now you see is 0.6 times 0.2. So you have that, and that is roughly going to be 0.625. So if I pick a smoker at random, what is the probability that I picked a male? 62.5%. So that's that. There's another way you could do this, of course. Is this kind of too far to the side? Maxwell effect. Okay. All right, let's look at another way, because I told you could do it a couple ways. table. Given the same data, we can actually construct a table. So let's actually do that. And again, we're going to break things up the way we're told. So we can do male and female, and we can do smoker and non-smoker. Now, ultimately, you can choose, assume a population of 100. So the numbers can be thought of as percentages. Because that's what percentage means, right? Out of 100. Percent per century out of 100. Right. So now male, we know that they're 40%, which means in a population of 100, the male row should add up to 40, while the female row should add up to 60 for a total population of 100. So that's where we're going to put the total over here. And then we're going to put a total over here. So now what we can do is now we start to look at all the numbers that we know. So we know that if we're a male, that there is a 50% chance that we're a smoker, which means that there are 20 male smokers in this population if there are 40 males in total, right? And this is just going to be the 0.5 times the 0.4, or the 50% of the 40%. All right. Which means that there has to be 20 males left over here to add up to 40, right? Then now of the females, we know that 20% of them smoke, which means if I take 20% of the 60%, that will give me the smokers. So I'm going to take 0.2 times 0.6, 6 times 2 is 12. So that's 12 female smokers in this population, which means that there are 48 female non-smokers. So the total number of smokers is 32. And the total number of non-smokers is 68 in this population. So now, that is a fully filled out table for this situation. I can go to what we want. Well, the probability that given that we took a smoker, what is the probability that they're male? Now, the probability of male given smoker is going to be the probability of male and smoker over probability of smoker, right? Or you can think of this as the size of M and S give over the size of the S. So this is going to be what? Well, who's male and a smoker, right? So that's going to be, see red here, that set of people. These are the males and smokers. So there are 20 people in that group. Out of how many smokers in general? Well, that's this group here. Uh, 32. So it's 20 out of 32. Now, I want you to appreciate something. Where did that 32 come from? And where did that come from? I want you to realize that the 20 came from us multiplying the 0.5 times the 0.4. So this was the 0.5 times the 0.4. And that's what gave us the 20. Now, if you look at the smokers, what gave us that? That's 32. Where did that 32 come from? It came from adding the 20 and the 12. Where did the 20 and the 12 came from? Well, the 20 and the 12 came from 0.5 times 0.4. And I added that to 0.2 times 0.6. That should be let's write this 0.6, write it in percentage form over here. Okay, so the numerator is 0.5 times 0.4. Hey, that was the same numerator we had last time when we did the tree diagram. And the denominator is going to be 0.5 times 0.4 plus 0.2 times 0.6. And hey, that's the same denominator that we had last time. So I know these answers are equivalent. They're going to give me the same thing. This might be exactly 0.625, but I don't know for sure. So that is the probability. Okay. So that's how you could figure it out with a table, a tree diagram, or a table. Yeah. What I want to do now for you guys is actually want to derive a formula for doing this. So maybe your tree diagram is going to be very complicated. Maybe you don't want to do a table because there are too many things to talk about. Or maybe you just prefer thinking in terms of formulas. You don't like drawing pictures. Whatever the case is, we're going to derive a formula for this. Okay, so that's what we're going to do. And the title of this lecture kind of gives is a spoiler alert. It gives away what I'm about to show you. So no surprises there. Let's throw a form for the above. Let B be a set and let A be some other set. Right? So B is a set that we care about, and A is any other random set. It turns out we can write B as B is equal to the part of B that intersects with A union the part of B that does not. So I can split a set into two parts, any set into two parts based on its relationship to some other random set. And you can see this in a Venn diagram, not as a proof, but just to illustrate. B intersected with A is going to be this part right here. And then B intersected with A complement is going to be this part right here. Notice that I can think of the set B as being the red portion and the green portion union together. And so that's where this equation comes from. It makes sense, right? So if I have a set B, I can split it into two parts, split it into the people who are also in A versus the people who are not also in A. And either of these sets could be the empty set. I'm not saying that there has to be something in there, but that is true for sure, okay? I also want you to note something further. B and A and B and A complement are disjoint. They're disjoint sets. They don't actually connect to each other. Because if you're in A, you're not in A complement. You can't be in both A and A complement at the same time, right? So basically what this means is that if I want to find the probability of some set B, it is going to be the same as the probability of that set intersected with some other set, union that set intersected with the complement of that other set. And then this means this follows by axiom 3 that says when you have the probability of a union of disjoint sets, the probability is going to be the sum of probabilities. So we have that, right? So basically this means that is true. Now, I'm going to actually rewrite these guys as something else. Where I'm going to use the same kind of logic that we actually used earlier, by the way, that I used up here in green right here. Okay, so what I'm going to do is I'm going to look at the probability of B given A. I know that is the probability of A and B over the or let me write it like how I write it here. It doesn't matter, but probability of B and A over the probability of A. This means the probability of B intersect A can be thought of as the probability of B given A times the probability of A, right? By that same reasoning, I can rewrite this guy. I can say, well, probability of B given A complement, well, that's the probability of B and A complement divided by the probability of A complement. So this means the probability of B and A complement is the probability of B given A complement times the probability of A complement. So then this formula becomes the following. So I can write this as the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. So the probability that the event B occurs, well, it can occur given that A has occurred, or it can occur given that A has not occurred. It can occur in either situation in general. And that's what that statement is saying. So essentially, don't forget what this was. This is the probability of B, right? That's what we were looking at before. So this here is a very important formula. We will refer to it as Bayes' theorem, or its rule. Some people call it Bayes' rule, some people call it Bayes' theorem. And we will call it version 1. It's unofficial, that's not. Right. I just want you to remember these two formulas, actually. I'm going to give you two formulas for Bayes' rule. I want you to know both of them. So I'm going to call it version 1 and version 2. Most people, when they think of Bayes' theorem, will think of version 2, which I'm going to tell you about right now. So now consider probability of A given B. Okay, where are we going to consider it? We know that probability of A given B is the probability of A and B over the probability of B. Right now, the probability of A and B, I can use a similar trick to this, and I can rewrite that as the probability of B given A times the probability of B. And this part is by definition of probability of B given A, right? Probability of B given A is the probability of A and B over the probability of A. Probability of A and B over the probability of A. So that should be an A. Right? And then if I look at probability of B, I can use this formula that I derived up here. And I can write that, well, that's the probability of B given A times probability of A. So B can occur given that A has occurred, or B can occur given that A has not occurred. And this is by version 1. So this leads to a very important formula. The probability of A given B is the same as the probability of B given A times the probability of A over the probability of B given A times the probability of A plus the probability of B given A complement times the probability of A complement. This is the next important formula, and this is called Bayes' theorem. A lot of people also call it Bayes' rule. This is version 2. That's unofficial. And this is what most people think of when they think of Bayes' theorem, by the way. What most people think of. Is our version 2, right? So if you look up Bayes' theorem in a textbook or something, or on Wikipedia, this is the formula that you're going to see. What I do want you to notice is the following. Basically, this says if I want the probability of A given B, but I actually know the reverse, the probability of B given, come on, iPad. But I actually know the reverse, the probability of B given A, I can use the probability of B given A to get to the probability of A given B. And that is important. You'll notice in our problem up here, that's exactly what happened. We were given probability of S given M, but we wanted probability of M given S. Notice that we had information on the opposite conditional. So it turns out we can use this formula we just derived to actually answer the same question again. So let's actually do that. Back to the original problem. So what were we given in the original? Let me recopy some things here. We were given the probability of M, that was 0.4. We're given the probability of not being M, 0.6. We're told the probability of S given M, which is 0.5. This means the probability of S complement given M is 0.5. We were told the probability of S given M complement, that is 0.2. This means that the probability of S complement given M complement is 0.8. And notice that we want the probability of M given S, the probability that we found a smoker. But then what is the probability that if we choose from the smokers that we chose a male? You will notice that you are given the opposite. So this is one situation in which you'd want to use a formula like this, a formula like Bayes' rule. You want to find a conditional, but you actually know that a conditional of the same events, but in the opposite order, right? And so we can do that now by Bayes. The probability of M given S, well, that's going to be the probability of S given M times the probability of M over the same probability of S given M times the probability of M plus the probability of S given M complement times the probability of M complement. Now we can go in and we can plug in all these numbers. So the probability of S given M is 0.5. Probability of M was 0.4. That's going to be the same, 0.5 times 0.4 plus probability of S given M complement is 0.2 times probability of M complement is 0.6. And at this point, it's like, gasp. This is what we got last time. Which seems like forever ago now, but if you look at that fraction and look at the fraction that we figured out by doing the tree diagram or the table, you'll notice that it's exactly in this formula. This formalizes that process of thinking, that way of thinking. So yeah, we'll get the same answer. So you can do it the diagram way, but you could also just realize that I want a conditional probability when I know the condition in the opposite order. So in that situation, I can use this formula. And it would be equivalent to me going through and painstakingly separating everybody into their own little box and then finding the probabilities. All right, so that is Bayes' theorem. Now, at this point, that's what we want to wrap up with, but I will leave you with a problem to try. Let me do it on the other one. So try this for next time. And that is problem 1 on this new problem set that I'm giving you guys. So of course you can try the others as well, but at least try this one. Okay, and of course, spoiler alert, you're going to use Bayes' formula to do that, but you should do it. As well as you could also use a tree diagram or a table. You can compare which one you like more. But that's what we have for today. That is going to be where we're going to wrap things up.
Professor,
Yeah,
I just
yes.
had a quick question. So, about the project. So I'm just a little confused with like the Python and how to do like R squared and beta and everything.
Okay.
I guess a question off the bat is like, do you have any good recommendations of where like we could learn this stuff?
No, all over the place. Google, Stack Exchange is usually a good place to check, but you could just literally Google it usually. Like anything you want to do, you can just Google it. How to find R squared in Python. And
I know. I mean, I tried that, but you don't have any like specific websites that you use that you think are really good.
no, I don't really have a particular website. If I don't know how to do something, I normally just do that and look it up in the moment. It might also be helpful to do the same thing in YouTube, and you'll see people actually typing it out for you and doing it. And you find a way you want. But yeah, essentially, once you figure out what you want to do, then if you don't know how to do it in Python already, I would just Google it. I don't really, I can't really think of a general resource off the top of my head that I would always go to, but I would tend to click on links that say Stack Exchange.
Stack Exchange?
Yeah. StackExchang. It's like a forum. So people will ask questions about stuff they're trying to do, and then a bunch of people will answer it. You can see you'll see a bunch of people answering the same question in different ways, and so you can see which way you would like more. So you're not really stuck to one method. So the forum is useful. Sometimes I'll do that.
Okay.
But as for a general resource, not really. And I'm not sure I tend to prefer that, because when you go by one resource, you just have like one person or one group of people talking about how they like to do it. But there are usually multiple ways to do things. So I like knowing about multiple ways to do things. So I would, do straight up Google or YouTube.
Just as another question, like I'm just a little confused on what to look up, like in concern or like in relations with the project in Python. Like I don't really know like what I'm looking for.
Yeah, so if you designate someone, or maybe you can all do this, to just kind of figure out what would be the things that we want to do, right? So if we're actually doing statistical analysis, how is that done? What are the important numbers to find? How many samples do we need? If we're doing any, like, how do you do it? Like, there are also resources on that as well.
All right.
And
I'm still a little confused, but I don't know. Would you say this is more of like you have to do it on your own in this project, more than like stuff that we've learned in class?
Half and half. If you're doing project 2, there will be a lot more to learn on your own. Project 1, not so much. In project 1, I think a lot of the statistics are actually done for you, because project 1, you're looking at mutual funds and stuff like that. They normally have the statistics on whatever website you're looking up, right? So if you look up a certain mutual fund, they'll tell you this is how it was doing over the past 5 years or the past 10 years since inception, right? You'll be given statistics. This is how it did on average. This is how it, right? So you don't actually have to know all that stuff. And I don't think project 1 requires that much statistics. It's more about probabilities and projecting with the financial math equations that I gave you before.
Okay.
You're telling a couple to invest their money over time, and they want to get a certain kind of return, right? So that's like a future value of something that you're competing, right?
Okay.
So it's more, project 1 is more probability and financial math. I don't think you'll need too much statistics. Like, you'll use statistics, but it'll be done for you, that you can make the decision. In project 2, you have to do your own statistics. And that's where you worry about averages and R values and box plots and all these things, because you are manually doing the comparisons yourself.
Gotcha. And then just lastly for project 1, how much of like Python do you think we should have in our final papers?
It's up to you. You have the freedom. Like, you make your choices and just justify your choices.
Gotcha. All right.
And you don't necessarily have to do Python, although I probably want you to. You could use Excel, especially for project 1. Excel should be plenty good enough.
Okay.
So yeah.
All right. Thanks.
All right. We will end right there. Thank you for your time and attention. I will see you guys in the next one. Ciao.